Alright, thanks for watching, and let's continue our analysis extravaganza by discussing the notion of continuity. And more precisely, today let's show that the following function is continuous. So show f goes from R to R, and I explain this notation in a second, where f of x is 2x squared plus 1 is continuous, let's say at the point x naught. Now, what does f look like? Well, it just looks like the parabola, but shifted up by 1. So maybe like that. This is f, and maybe this is 1. Now, what this notation means is simply, here R is the domain of f. So when we write x, we usually assume x is in the domain, and this R is the codomain. And all that it means is that if x is a real number, then 2x squared plus 1 is guaranteed to be in R. Of course, here more is true. We know that f is in 1 comma infinity. But this is just a promise. If x is in your domain, f of x is guaranteed to be in R. Now, what does continuity mean? Well, intuitively, let's say if this is x naught, so some fixed point, x naught, and let's say this is f of x naught. Intuitively, all this means is that if x goes to x naught, so if you have a point x very close to x naught, then f of x is also very close to f of x naught. So in other words, if x goes to x naught, then f of x goes to f of x naught. In other words, if the inputs are close together, then the outputs are close together as well. Now, the question is, what does goes to mean? And it turns out there are two different ways of interpreting this that are actually equivalent. And I'll talk about both of them. Now, one way to think about continuity is with sequences. So here's the first definition. Namely, f is continuous at x naught if whenever you have a sequence xn going to x naught, so if whenever xn is your new domain and converges to x naught, then f of xn converges to f of x naught. Which is nice because we know what limits of sequences are. And that was again the whole point of chapter 2 and the previous playlists. So again, picture-wise, all it means is that here you have your function f. And let's say this is again x naught and f of x naught. All it means is that whenever you have a sequence xn converging to x naught, then f of xn converges to f of x naught. So again, this idea of if xn goes to x naught, then the outputs go to their respective outputs. And using this definition, let's show that f is continuous. So, and by the way, how do you define continuity in general? F is continuous if for all x naught in the domain, in the domain of f, and f is continuous at x naught. In other words, if it's continuous at every point in the domain. Alright, and now with this definition, let's show that f is continuous. So here, again, let x naught be given, and suppose xn converges to x naught, And the idea is we want to build up to f of xn goes to f of x naught. And the nice thing is we have actually done all the work before, because in a previous video, I believe, we've shown that if xn goes to x naught, then xn squared goes to x naught squared. Okay. And again, just to emphasize, this is as n goes to infinity. And then xn squared goes to x naught squared, and therefore multiplying this by 2. Okay. So 2xn squared goes to 2x naught squared. And lastly, adding 1 to this, we get 2xn squared plus 1 goes to 2x naught squared plus 1. And therefore, f of xn goes to f of x naught. And therefore we've done. We've supposed that xn is a sequence converging to x naught. You show that f of xn is a sequence converging to f of x naught. So this is the, if you want, the sequential definition of continuity, but the problem is it's not very practical, because it turns out in some weird, more advanced spaces, you don't always have sequences and convergent of sequences. And you kind of want to replace this with a little better notion of continuity. All right, and now let's do the second definition of continuity. It's a little bit harder to understand, but it is more direct. It doesn't use limits of sequences or whatsoever. So, definition 2. Namely, f is continuous at x naught. And that should remind you a lot of the definition of a limit of a sequence. So, if, no matter how small your error, so for all, epsilon greater than 0. And let me draw a picture, because it's very important in understanding this scenario. So here you have f, maybe like here, and this is x naught. Maybe this is f of x naught. Now, because you have an error, just like for sequences, you have this good region. Namely, the region centered at f of x naught, and radius epsilon. Okay. And radius epsilon, and this is again good. You want to be inside here. Right? And here's the thing. Before, we let n go to infinity. So we wanted n to be very large. Here it's the opposite. We want x to be very close to x naught. So this is x, and this is f of x. So before, our threshold was very large. Here, our threshold is very small. So we want x to be at most delta away from x naught. So, no matter how small the error, there is some small threshold. So it's delta, positive, and think of it small, such that for all x, okay, if you're at most delta away from x naught, in other words, if you're in this region here, centered at x naught and of radius delta. So in other words, if x minus x naught is less than delta, then f is in the good region. Then f of x minus f of x naught is less than epsilon. So to reiterate, no matter how small the error, there is some small threshold such that if x is within that threshold, then f of x, so here f of x is in the good region, which remember is the region in blue. This thing. In other words, if you get close enough to x naught, then f of x is close enough to f of x naught, meaning that f is entirely inside the good region. So if you ignore anything that happens outside, then you say, okay, f is good. It's very close enough to f of x naught. And this is no matter how small the error is. Even if epsilon were 0.001, you can eventually be in the good region just by letting x to be very close to x naught. Alright, and with this, let me now prove that 2x squared plus 1 is continuous. So, let's show f of x, which is 2x squared plus 1, is continuous at x naught. And okay, so the following problem is slightly difficult, but the thing is, once you see it once or twice or 25 times, then there is some threshold where you start understanding it. Now, just like remember how confused you were with sequences. It was very complicated, but then the more you did it, the more it made sense. And for this, we need some scratch work. So part 1, scratch work. So what do we want to show? We want to show that f of x minus f of x naught is small. So ideally, we want this to be less than epsilon. Okay? And now let's just do some algebra to calculate that difference. F of x is 2x squared plus 1, and this is minus 2x naught squared plus 1. And that becomes 2x squared plus 1 minus 2x naught squared minus 1. Great, this already cancels out, and then a 2 factors out, and you get a 2x squared minus x naught squared. And remember, a squared minus b squared, it's a minus b times a plus b. So x minus x naught times x plus x naught. And what we want this to be less than epsilon. Now notice, this is good, this x minus x naught, because this is the term we have control over, because we can just let this to be less than delta. This is the thing we want to control. So we already have power over this. This is the thing we want to have power over. Kind of like, think a king wants to just get more countries in some sense. Okay, now the goal is let's estimate this. So this absolute value of x plus x naught. Okay. So, well, we want this to be less than something, so let's just use a triangle inequality. So this is less or equal to absolute value of x plus absolute value of x naught. And ideally, we want this to be less than some form of epsilon. Maybe epsilon over 2, we'll see. However, there's a problem. Because x can be very large. You see, and if x is at 9,000, there's no way to get this less than epsilon. That's why we really have to use the fact that x is very close to x naught. Because what do we have? This is x naught, this is x. Well, it's okay to assume that x is at most 1 away to x naught, because x is supposed to be very close. So if, let's say, and remember this for later, so if x minus x naught is less than 1, then we can actually estimate those absolute values, because, again, this is x minus x naught is less than 1. However, we need an identity that involves absolute values, so let's use our most hated identity, which is the reverse triangle inequality. So this is greater or equal to absolute value of x minus absolute value of x naught, absolute value. And again, it's not gibberish because here we have absolute values. That's why we need to use this. And moreover, absolute value of a number is always bigger than or equal to that number. So what do we get? Absolute value of x minus absolute value of x naught becomes less than 1. So this thing. equals less than 1, meaning that absolute value of x is less than absolute value of x naught plus 1, which is great because this is fixed. And therefore, what do we have? X plus x naught, again, less or equal to x plus x naught. But now we have this, so this is less than x naught plus 1 plus x naught, and that becomes 2x naught plus 1. Which is great. It is constant. It does not depend on x. And in particular, we'll see this will help us to do our proof. Then, now let's go back to our original thing. What did we try to estimate? We had, f of x minus f of x naught. We found something like 2 times a good term, and then that bad term. But now we know this is, let's say, less than or equal to 2 times the good term and some constant term, 2x naught plus 1. And we want this to be less than epsilon. But now it's easy. We can now literally just solve for x minus x naught. So in other words, this implies x minus x naught is less than epsilon over 2 times absolute value of x naught plus 1. And again, this is good because this does not depend on x. We want something that might depend on epsilon but does not depend on x. And therefore, this gives us a delta. All right, and now with this, let us show our proof. So now we have done the hard work, so now it's party time. So step 2, our proof. So let epsilon be given. And let delta. Now, you might be tempted just to say delta is epsilon over 2 times 2 absolute value of x naught plus 1. However, remember from long time ago we had this other identity. We said that we needed x to be at most 1 away from x naught. So, which suggests that we not only choose delta to be this, but delta to be something involving 1 and epsilon over the gibberish. And before, remember we had capital N was the maximum of 2 things because we wanted capital N to be large. Here we want delta to be the minimum of the 2 because we want delta to be small. So choose delta to be the minimum of those things. Then if x minus x naught is less than delta, then for sure it is less than 1 and it is less than this gibberish. So if something is less than the minimum of the 2 numbers, it's less than both of the 2 numbers. Then, so x minus x naught is less than 1. And remember, a consequence we found is that x plus x naught is less than, I think, 2 times x naught plus 1. Okay. And then, what do we have? Remember we calculate f of x minus f of x naught. Okay. And ultimately we found that it is 2 times x naught minus x times absolute value of x naught plus x, which is less than or equal to 2 times x minus x naught. And then we find that f of x minus f of x naught, that is, remember, 2 times x minus x naught times absolute value of x plus x naught, which is less than or equal to 2 times absolute value of x minus x naught times absolute value of x plus absolute value of x naught. However, remember, now we can just use this identity. So this thing is less than 2 times x minus x naught times 2 times absolute value of x naught plus 1. And now use the fact that delta is smaller than this. So x minus x naught then becomes smaller than 2 times this thing, epsilon over 2 times absolute value of x naught plus 1, and then 2 times absolute value of x naught plus 1, and then lo and behold, this is a beautiful thing about epsilon delta proofs. This cancels out, and you're left with epsilon. The epsilon of victory, and therefore we are done with this proof. So the function is continuous, and next time I'll show you that those two definitions are equivalent, and then in the rest of the playlist I'll do more examples and consequences of continuity. All right, thank you very much.